all the yes, sir. So, with the permission of all the respected personalities present here with us today, and also the presence of our respected speaker, I would like to initiate the webinar session titled as Determination of the Carbon Source Sink Characteristics of a Forest Ecosystem. So, before I begin, I would request all the viewers who are not participating to please turn off their cameras and microphones throughout the lecture. Good evening, ladies and gentlemen. I am Ritanuka Ghosh, a member of Geological Institute, Presidency University, and I shall be your host for the day. It's an urgent request to all the attendees that if you can, then please keep your cameras and microphones off to avoid noises and interruptions as much as possible. We will also have a question answer session at the end of the lecture so that you can post questions in the chat box of the Google meeting during the talk, which will be conveyed to our speaker at the end of the session. For the people who are viewing us on YouTube Live, we request you to please post your questions in the live chat thread and we will collect that after the lecture ends. On behalf of Geological Institute, Presidency University, Kolkata, I would like to take the pleasure to welcome you all to today's lecture. We are undoubtedly very fortunate to have with us Dr. Supriyo Chakraborty, who has agreed to devote some time from his busy schedule to this webinar today. He is currently a senior scientist and is the head of the Mass Spectrometry Group and the MetFlux India project at the Indian Institute of Tropical Meteorology, Pune. He was graduated from IIT Kharagpur and earned a master's degree in exploration geophysics. His work is mainly focused on monsoon reconstruction using the natural archives, isotope hydrology, moisture dynamical processes, ecosystem GHG fluxes, and energy transfer processes at various natural ecosystems. We would love to hear more about him. So now I would like to turn to none other than our very own Dr. Nilanjan Dasgupta, Professor of Geology, Presidency University, to please call Dr. Supriyo Chakraborty to the dais. Sir, can you please take over the mic?
Sure. Thank you, Ritanuka. Good evening to everybody and my students. Dr. Chakraborty, welcome to this platform. As Ritanuka has already partially introduced you, and we have been talking all the way, and we have been introduced to each other informally. But I would like to introduce Dr. Chakraborty on this dais. Dr. Chakraborty, as we heard from Ritanuka, graduated from IIT Kharagpur in geophysics and then did a PhD degree in geology from MS University, Baroda. He has worked on several aspects involving monsoon reconstruction, isotope hydrology, moisture dynamics, greenhouse gases. His publication list is endless. He has 80 peer-reviewed publications to his credit. He has mentored several PhD and has guided several MSc dissertations. He has been an active member in popularizing his research and this field of science amongst students and laymen like us. He is the recipient of the Certificate of Merit Award by the Ministry of Earth Sciences, Government of India. He is a coordinating lead author and an editor of the book Assessment of Climate Change over the Indian Region, a report of the Ministry of Earth Science, Government of India, published in 2020 by Springer, Singapore. Today, as Ritanuka said, Dr. Chakraborty will speak on determination of the carbon source sink characteristics of forest ecosystem. I'm really I must express that it's unfortunate not to have heard you in person in our Heritage Institute, Dr. Chakraborty, due to the protocols that are presently being imposed. But we honestly hope, and you have also promised that you will visit our department on 1st of December. We'll be ready to receive you on that particular day. As the on-campus presence of all these students are not yet achieved on every day, It will be really a pleasure to have you in our department and meet some of our students and scholars who will be present on that day. I would not take any further time because our students are eager to hear you, Dr. Chakraborty. And I invite you to this virtual dais and I request you to deliver your talk. Dr. Chakraborty, please. Thank you.
Thank you, Dr. Dasgupta, for giving introductions. And I also like to thank Sayantika and Ritanuka for introducing me in this forum and inviting me to present our work. So I will directly go to present my slides.
Is there any problem with?
I think, sir, he's facing some network issue.
I got disconnected.
Yes, sir.
Now,
is it okay now?
So echo is coming?
Yes. Is it okay now?
So we can hear you, sir.
Okay.
না না এটা এখানে মিটিং আছে তো এই পরে একদম উপরে থেকে এই গ্রিনটা এবার তুমি প্রেজেন্ট স্ক্রিন করে দাও পড়ে এক আমার স্কুলে টপ করে দাও হ্যাঁ শাট ডাউন জি স্যার শেয়ার হচ্ছে কিনা
Can you see my slides?
Yes, sir.
Okay.
Play just.
Can you see my slides?
Yes, sir. They're perfect.
Okay. So before starting, I would like to tell you that if you have any questions, so please do not hesitate to interrupt, because I would like to present in such a manner so that I can convey some message and people have some kind of understanding, because I understand that most of the participants, they are young, so that, and I would like to give a message that I can present in a manner that they can understand to some extent. So please don't hesitate to interrupt me. Now, what you see here is that this is, schematic diagram of a forest, and we know that the forest, it absorbs a lot of carbon dioxide, and this absorption is shown here by these dark arrows. So where huge amount of carbon dioxide is absorbed by forest, but at the same time they also release substantial amount of carbon or carbon dioxide through the process of respiration. So if a forest or an ecosystem absorbs more amount of carbon dioxide and releases less amount of CO2 through respiration process, then we can tell the ecosystem is acting as a sink of carbon. But it may so happen that some forest ecosystem may absorb less amount of carbon dioxide and relatively release more amount of CO2. So in that case, the ecosystem will act as a source of carbon dioxide. Now, this, whether it is a source or sink of carbon dioxide, that can be understood only if we make some measurements. Measurements in the sense we have to quantify how much carbon dioxide is being absorbed and how much carbon dioxide is being released. So the difference will tell you whether it is an active source or active sink of carbon. Context of global warming, this is very important because we know that anthropogenic activities are releasing huge amount of carbon dioxide, and we know that and a part of this carbon dioxide is being absorbed by biosphere, that is plants and trees, and partly it is absorbed by ocean. And terrestrial biosphere plays a very important role to absorb these carbon dioxides. However, with the changing conditions, that is with rising temperature and environmental conditions, the capacity of forest of absorbing this carbon dioxide does not remain constant. It may change. And how, in what direction it will change, whether it will have more capacity or less capacity, we cannot predict unless we make some measurements. For that, a long-term measurement is there, which will be able to actually quantify what is the capacity of forest, or we can say what is the carbon sequestration potential of a forest. Now, other than carbon, the plants also releases huge amount of moisture, which it takes through the roots. Basically, soil moisture is taken and then it is released through the process of evapotranspiration, which is shown here by these H2O wavy lines. So, we'll be talking mostly about these carbon transfer processes, and particularly a specific forest in Northeast India, which is the Kaziranga National Park. So the title of my talk is Determination of the Carbon Sourcing Characteristics of Forest Ecosystems in general, and then I specifically tell about the Kaziranga forest. So these are my collaborators which are also actively involved in this project. And this is one of the forest and these pictures what we have taken during a field trip in 2019, which shows that Kaziranga forest is basically very rich in biodiversity. It has various kind of animals like rhinos and elephants and even Royal Bengal tigers and many more. So the outline of my talk is given here. Firstly, I will describe about this carbon exchange process. Then I will tell about the terminologies, then the sourcing characteristics, boundary layer processes to understand how we measure this quantity and how it is controlled by boundary layer processes. Then I will describe briefly about eddy-covariance technique, which is used to quantify these carbon transfer processes. Then the vegetation pattern of Northeast India, and the case study means how we are working this in Kaziranga National Park area. Then I will summarize this talk. Now this is little bit about the carbon cycle in plants. So probably most of you know from your school curricula that the photosynthesis process requires sunlight. So under the sunlight or when this abundant solar radiation is there, this carbon is absorbed by plants and then it makes its own food. So then this carbon, whatever synthesized food, there's a cellulose or sugar, which is transferred to the different components of the plants. For example, from leaf, it goes to the stem, then it goes to the root, and afterwards, then when this, at the same time, it also releases carbon in the form of respiration during the process of respirations. But there are two kinds of respiration. One is
So,
He's probably facing some internet issues.
some internet issue. Can you hold a second?
yes,
It's
sir.
okay. It is okay right now, Dr. Chakraborty.
Is it okay now?
Yes, sir.
Okay. Actually, somebody called me in my phone, so there is a problem. So there are two types of respiration. One is autotrophic respiration, that is purely driven by the plants, and then this another type of respiration, that is soil respiration, which is driven by the bacterial activities and mostly degradation of the organic matters. So, and it may so happen that the total ecosystem respiration is called by the we have to consider both kind of respiration, that is autotrophic respiration and heterotrophic respirations. Now, whether it acts as a source or sink, we have to consider in this respect, that is total amount of carbon absorbed by photosynthetic process is exceeding the total amount of respiration or not. So if it exceeds, then only we can say it is a sink. But it may so happen that sometimes respirations other than this autotrophic respiration, heterotrophic respiration may play a significant role. So in that case, the total amount of respiration may exceed the total amount of carbon absorbed. But in that case, the forest ecosystem may act as a source of carbon. So particularly, this point is very significant, especially in the context of Kaziranga National Park, which I will come later. Now, there are few terminologies which needs to be understood. One is that net ecosystem exchange. Now, as I mentioned that there are two components. One is photosynthesis process, one is respiration process. And net ecosystem exchange, it is actually the net system. That is how much carbon is absorbed and how much carbon is released. So this is what is called net ecosystem exchange. And so the definition is the net amount of carbon exchanged between the land biosphere and the atmosphere. And when it is negative, so that means it is absorbed. That is, it is a sink process. And the positive means it is being released. So from atmosphere to biosphere, so we call it a negative flux, negative CO2 flux. And when it is other way, that is when it is released by respiration process, it goes to atmosphere. So it is considered as a positive flux. It is just a sign convention, nothing else. Now, RECO, it is the total ecosystem. Eco means ecosystem respiration. So total ecosystem respiration. So it is both by the autotrophic process of respirations and the heterotrophic process of respirations. And so it contains above ground plus soil respiration. So above ground means it is mainly by the trees, by all the trees, and soil respiration is mainly by the bacterial process. So, and sometimes it may so happen that soil respiration contributes up to 90%. What is shown here is total range. The range is about 30 to 90%. So it actually one of the determining factors whether an ecosystem is acting as a source or sink. Now there is another terminology. This is called gross primary productivity. So, so arithmetically it can be written as minus NE plus RECO. So if minus NE means, as I told you, that when carbon is absorbed, we denote it as negative sign. So GPP will be minus NE plus RECO. So in that case, but GPP, please note that GPP and RECO, they are always positive. So in this case, if NE is more than is quantitatively or numerically it is more than RECO, then GPP will exceed the RECO value. Otherwise, it may less than the RECO value. This part will be clear when I explain in the later in my talk. So here NE expressed in the simple form, that is FA. FA means the photosynthetically assimilation of carbon due to photosynthetic process, which is shown in green color, and the effort is the total ecosystem respiration, which is shown by red color. So FA and FR, unfortunately, they cannot be measured directly. So what we measure but through this eddy-covariance process, which I'll come later. So this is the net, that is difference between these two processes, photosynthetic process and respiration process. So in that case, actually, it poses an ill-posed problem. that is, we have one equation, but there are two unknowns. Two unknown means one is photosynthetic process, one is respiration process. So that's why there is some kind of uncertainty in these estimations that I will come discuss later. So conventionally, the green means it is the absorption of carbon dioxide, and red means it is the release of carbon dioxide. And the difference between these two, if absorption is absorption is more than carbon dioxide, so any will be negative, and it is a total amount, and the downward arrow means a total amount of carbon dioxide is going to the biosphere, that is from atmosphere to biosphere. But supposing it is other way around, but that is numerically, if this green arrow is less than the red arrow, then it will be other way around, that is net amount of carbon dioxide will be released and it will go to the atmosphere. In that case, it will act as a source of carbon. And also please note that the total numerical value, the source and sink characteristics, or the photosynthesis component and the respiration component, they can be much higher than their difference, that is NE. Sometimes it could be almost order of magnitude. Of course, it varies from ecosystem to ecosystems, but in some cases it could be very high. As I told you, at least 7-8 times. Sometimes it could be 2-3 times. So it also imparts some kind of uncertainty. So that's why what we measure actually it is not the realistic value, but as I will discuss later, eddy-covariance gives one of the best techniques to quantify the carbon sequestration processes. Now, there are which are the parameters which control this carbon sequestration process. So these are solar radiation, air temperature, there are physical parameters and basically the weather parameters, and there are biophysical parameters, that is one is leaf area index, and then the plant type, and then the different other parameters. And rainfall, it plays a dual role. For example, without water, the plants cannot do their physiological processes. So they need adequate amount of water which comes through the soil. But if rainfall is, supposing if it rains too much, then it can have some detrimental effect on photosynthetic process, because we know that during heavy rain condition, cloud cover increases, which will inhibit or limit the solar radiations, and so that is one way it can affect the photosynthetic process. And other way, when it rains very heavily, it can also it may damage the stomata, through which carbon dioxide is absorbed. So due to some damage in stomata, photosynthetic process may also be reduced. So that's why rainfall plays a dual role, and I will discuss a little more detail later at my talk how exactly it controls the photosynthetic processes. Now, in order to understand the eddy-covariance technique, which I'll discuss a little later, so I would like to give you a little background about the atmospheric processes, particularly atmospheric boundary layer processes. This, as you know that it is the lowest part of the troposphere which connects surface to the atmosphere. So what is shown here in this slide, that the lowest part, it is about the just above the Earth's surface. This extends from about 1 to 3 kilometers, where the processes are very highly turbulent, and this turbulence is basically controlled by the solar radiation, more specifically by the solar radiation which is being emitted from the Earth's surface. So the nature of surface, for example, if it is surface is covered by vegetation, particularly in forest ecosystem, so emitted radiation will be less, and if it is in urban area, emitted radiation will be much higher compared to a forested ecosystem. So that will determine the surface temperature. So, and that will also, and since this flux also depends very heavily depends on the wind velocity, particularly the vertical wind speed. So wind velocity also depends on the temperature, and hence it depends on the boundary layer processes. And one more thing is to be noted here, that all the energy which drives the weather and atmospheric circulation, it comes through the planetary boundary layer. And another important point is that what is happening in the boundary layer and what is happening in the free troposphere, generally they don't know each other. Means very loosely speaking, they don't know each other, what is happening. Free troposphere may not be knowing what is happening in the boundary layer. So they are sort of isolated systems. So, but this boundary layer, this height varies. Actually, it varies on a diurnal scale. For example, during the night time, this boundary layer comes down close to the surface, and in that process, it traps the pollutants. But with the when after the sun rises, this boundary layer slowly expands, and then since mixing process is high, that is a turbulent process becoming high, so the boundary layer slowly mixing will be very high and boundary layer will extend, and in that process it actually controls the mixing process. So how the exchange takes place? So we know that radiation is one of the processes, and then conduction, diffusion, advection, and turbulence. So these are the processes which have exchange of carbon between atmosphere and biosphere. Now, turbulence is the most important feature of the boundary layer, and it is actually responsible for, and which is actually million times more efficient than conduction and diffusion. So these processes also exchange carbon, but their contribution is very, very small compared to turbulent processes. So that is why we have to understand how turbulence control this kind of exchange, and then in order to quantify the turbulent process, what kind of instruments and we need, that I will discuss a little later. Now, to tell you a little more about the turbulent processes, this slide shows two parameters. One is temperature and one is wind. The wind is shown by the red line and temperature is shown by blue line. Now, what we see here, they have a very high covariation. Since wind is one of the component which is used as turbulent process, so what we can say here is that this also control or gets controlled by the temperature. And temperature here means it is basically the surface temperature which is controlled by the emitted solar radiations at a given place. Now, in the second figure, what we see here is that three wind components. One is U, the horizontal U component X direction, V, horizontal wind component Y direction, and then vertical wind component is denoted by W. Now, what we see here is that U component is the highest, and V component is quite smaller than U component, and W component, it is very, very small with respect to both the U and V component. And at the same time, if we take an average, let us say if we take 30 minutes average or so, W component is almost constant. What we see here, that W component, that is green line, it is almost parallel to x-axis. So that means it hardly varies. But despite being it is a constant, the exchange takes place. So that is what we have to understand. So a little longer time scales, 30-minute time scales, we see the wind speed is almost constant. But if we consider in a very, very small time scales, for example, if you see the left figure, it is only 3-minute data, and we can see that this W means the vertical component. It varies. It shows a very significant variation. So that means on a very small time scale, W varies a lot, and this is the process. Actually, this high variation of wind, which is responsible for this exchange process. So now, I would like to just give you another example of the turbulent processes. If you measure the surface temperature at the Earth near surface, we will see this much of variation. For example, on 7th June and 8th June, you see there are significant variations. But if you go slightly above, approximately what is shown here, 1.1 kilometer, then if you measure the temperature, so in 8 June, 9 June, 10 June, see temperature is almost constant. So there is no variation in temperature. So simply means that it is the free troposphere. See, one in this place, this is probably in high latitude place. So troposphere is free troposphere is approximately 1.1 kilometer. But below that, it is atmospheric boundary layer, which is heavily influenced by the turbulent processes just above the Earth's surface. Now, what the eddy-covariance techniques, it is widely used to quantify the carbon and water exchange processes across the ecosystem and as well as in urban environment. So, I will just briefly describe you what is the principle of this eddy-covariance technique. Now, and these turbulent systems can be envisaged with it is consisting of many small and large kind of eddies, which is shown here, which is sort of whirling nature of the wind direction, wind pattern. So, which is shown here by these blue circular arrows. So they can vary from few millimeters to about, it can go up to about a kilometer or more. So that is why so these are called the eddies, and actually these eddies are responsible for exchange of this material, and from the material means in this is carbon dioxide and water vapor from atmosphere to biosphere. So if you consider one eddy at a time t1, and then it means, and C1 is the concentration of carbon dioxide, and W1 is the wind vertical wind speed. So at a given time, let us say the C1 stands for carbon dioxide concentration, and it is being carried by W1. Being carried means, so vertical wind, which is flowing from top to bottom, it is carrying carbon dioxide from atmosphere to biosphere. And then at the next moment, the CO2, which is released through the process of respiration, it is being carried from biosphere to atmosphere, and it is being carried by another wind, W2. So this concentration is CO2. So AD1 actually moves this one parcel of air, C1, down with speed W1, and AD2, it moves another parcel of C2 up with speed W2. So each parcel has concentration, temperature, humidity, and if we know this and the speed, we can calculate the fluxes. So what all we know, in principle, we must know what is C1, what is C2, and what is W1 and what is W2. And at the same time, we have to measure temperature, because temperature actually C1, C2, we measure the density or the concentration. And since it varies with temperature, so that's why we need to measure temperature. So if we measure these parameters, this wind speed, concentration, and temperature, we can calculate what is the CO2 flux. And similarly, if C is replaced by water vapor concentration, we can also measure the water vapor flux between these two reservoirs, that is atmosphere and biosphere. So here is the formula is given here. So in a turbulent flow, the vertical flux can be shown with this simple equation, that is rho d is the air density, and S stands for dry mole fraction, and W is the vertical wind speed. So, and if we take the average of this, generally averaging is take for about 30 minutes. So we can calculate actually manner, but we have to do a series of these calculations, and where we can get the ultimate value, what is given F at the bottom. So in the there is something, the technique is called Reynolds Decompositions. What it says is that so any component can be written in the form of the steady part as well as the fluctuating part. For example, we know, just to give similarity, we know that for example, we know that what is weather and what is climate. Generally, long-term average is called climate, and then fluctuation, when we have the fluctuation, then that is called weather. So in this case, what we can say is the long-term average is given by the average term. That is the fluctuation term, which is given by prime term. So this, so according to the Reynolds decompositions, so these can be, any component can be divided into these two terms. One is the average term and one is the fluctuation term. Then when we assume some kind of average, so and with some kind of simple derivation, ultimately we can express the flux in the form of the bottommost equation, where F equal to the density and then W prime and S prime, which is the fluctuation term. And actually this is the covariation between these two parameters. So Ws, we take the covariation of W prime and S prime and then multiplied by density, then we get the flux. So this slide shows the fluxes for these three different parameters. One is the CO2 flux, which is shown by, here is the green in equation in green, and then the sensible heat flux. This is shown by this red font, and then the latent heat flux. This is shown by the this blue font. So what we measure is that we measure these three components. One is for CO2 and other is this sensible heat flux and latent heat flux. Basically, they are water vapor flux. So water vapor flux, it can be decomposed into two components. As you know that latent heat, as from the high school physics, you know that when temperature change, when latent heat means when the total amount of heat changes but the temperature remains the constant. So in that case, so this is called latent heat. For example, during the monsoon time, a huge amount of moisture in the atmosphere, releases latent heat, and which actually warms the atmosphere. So, and this amount of this energy released through the latent heat process, it becomes, I mean, it can be comparable to the direct solar radiation. So this plays a very crucial role or critical role in maintaining the monsoon system. So, and sensible heat flux is the heat flux which actually can be measured. As I told you, latent heat, we cannot measure the change in temperature. But in case of sensible heat flux, we can change the temperature change. That's why it is called sensible heat flux. So the water heat flux, it has two components. One is latent heat flux and one is sensible heat flux. So this is decomposed into two components. So total heat flux in case of carbon. Now, if we consider only the carbon dioxide, so there are the total flux, or called NEE, means net ecosystem exchange. It has two components. One is FEC and one is FS. Now, FEC means it is driven by eddy or turbulent fluxes. It is purely turbulent flux, the turbulent process as I described a little ago. And then FS, it is the storage flux. Now, this is not controlled by turbulent processes, but there is always some amount of carbon dioxide stored within the canopy, and it slowly diffuses. It can go up, it can go down, but in general, its component is not very significant. With respect to the eddy-driven fluxes, it may be 5% or 10%. And the measurements of this storage flux, it requires different kind of instrumentations, and which is not always possible. So that is for that reason. So in most of the cases, storage flux is not measured. Though for accurate measurements, ideally it should be measured, but because of technical problems and other logistical problems, FS is not measured. So most of the cases, only the eddy-driven flux is measured, And so in that case, whatever we measure, that is actually a slightly underestimation of the carbon fluxes that is actually available in the nature. So how do we do flux measurements? So it requires sophisticated instrumentations. Turbulent fluctuations happen very quickly, and changes in concentration, density, or temperature are small, and they need to be measured at very fast and with great accuracy. So EC flux measurements are widely used to measure carbon dioxide, momentum, heat, and water vapor fluxes in the boundary layer. So here I show the components. For example, the solar radiation, which is denoted by Rn, and it is denoted in the downward direction. So, and then there are two water vapor fluxes. One is the latent heat flux, and another is the sensible heat flux, which is denoted by H. And then there is another small component, which is ground flux, so which is represented by G. So in that case, actually G is getting lost to the ground. So in general, what we can see here, if we subtract G from Rn, so Rn minus G should be or ideally equal to Le plus H. That is, it will give you a very simple energy balance equation, Rn minus G equal to Le plus H. And the right hand figure, it shows the schematically shows that how the eddies are controlling this kind of processes. So now the methodology, what we need here is that we need a tower, that is called micro meteorological observation is carried out in a tower which hosts several kind of sensors and equipments. And then there are of course other methods. For example, isotopic analysis are also used. Of course, it is not used directly it is not an alternative, but it is also supplementary method which can also provide some other information. Then other than the observational methods, there are process modeling, where you can model all the processes, and then you can calculate the GPP, and from there NE and RECO. And then of course there are remote sensing methods which remotely sense the various parameters, and it can also give you the GPP. So out of all these three methods, we generally rely on this what we have been carrying out using the eddy-covariance, that is direct measurements technique in an ecosystem. And process-based modeling, of course, it is a purely modeling approach, and remote sensing, it is a slightly different methods. But combining all these methods, we can have a better understanding of the carbon exchange process of any given ecosystems, and also in a country scale. Now, these are the instruments. For example, the left figure shows the sonic anemometer, and what is shown here is that this it is taken from a tower, and this tower is there in Darjeeling, which is of course currently not in use. And then right side, what we see here is the infrared gas analyzer. So this is the main equipment which actually measures the CO2 and water vapor concentration, and it has a thermometer also inside which can measure the temperature, which is actually used to make some correction, so that when density changes because of the changes in temperature, so we can correct, and we can get the true density or the concentration values. Then there is a pyrometer which can measure the solar incoming and solar outgoing, that is long wave radiation, incoming long wave radiations, and also outgoing long wave radiation. Outgoing means which is getting the radiation which is coming from the Earth's surface. And then it can also measure the short wave incoming radiation and then short wave outgoing radiation. So there are four components. You have there are two incoming components, one long wave, one short wave, and there are two outgoing components, one short wave, one long wave. For that you need four different sensors which is integrated into one instrument or one equipment, which is called the pyranometer. And then you have weather sensor. Generally, it is the basic weather sensors which measures temperature, humidity, rainfall, air pressure, and wind speed and direction. So these parameters are measured by this weather sensor. And then we have one very important sensor is used, which measures the soil CO2 fluxes. That is, how much CO2 is coming out, mainly due to the heterotrophic process. Of course, it may include autotrophic process. For example, the roots which are staying below the ground, they also respire. But most of the soil respite will be contributed by the bacterial activities. So the soil CO2 fluxes is a very important component. So that will give you the how much CO2 is being respired by the soil process. And then this another instrument which I show here is a CO2 Ch4 Isotope Analyzer. This is of course not of the eddy-covariance system, but if we include this data, if we get this data, the isotopic analysis of carbon dioxide or methane in this another gas, GHG methane, then we can have a different parameter, and of course we can have some other insights about the carbon dynamics process. Now, this figure shows the vegetation pattern in India. What we see here is that, for example, if we see the green color, so green color is, you know that the average forest density in India, overall India is something about 20 or 25%. It is relatively small amount compared to the required standard, which ideally it should be at least of any country should be covered by forest. But in general, India has significantly less than that. But if we consider the Northeast India, this region has much more forest cover compared to the rest of India. It is almost 64%. What we see here is that entire Northeast India is covered by almost by green. So, but and another thing is that maximum carbon sequestration takes place typically from monsoon to post-monsoon period. So what it means is that the maximum amount of productivity, that is carbon synthesis, it is throughout the process it is not the same, because it depends on water availability. Since water availability is most maximum during the monsoon and post-monsoon season, so most of the cases in India, the maximum carbon reduction takes place during the starting from monsoon to post-monsoon and early winter. It goes up to almost about November, December. But Northeast India, it shows a very different characteristics. So firstly, Northeast India has a much higher forest coverage than rest of India. So this is one of its characteristics. And secondly, the carbon sequestration pattern of carbon sequestration in Northeast India is different with respect to Northeast India. Now, what is the reason that I will discuss a little late. So what we like to discuss or what we study at Kaziranga National Park are given here in the form of bullets. That is, what are the seasonal variation of any GPP and RECO? Then how do they compare with other ecosystems in India? Then how do we improve the partitioning of any into its component? As I told you that we measure only one component any, and then through a different process, numerical process, any is decomposed into two components. The one is the GPP, that is total amount of carbon synthesis, and another component is total amount of carbon released through the process of respiration. So this is called the partitioning of NE. And then how the carbon and water cycle link together. So since we know that during the stomata, which actually takes carbon for photosynthetic process, and the same stomata releases water by process of transpiration. So in that context, both this carbon transfer process and water transfer process are very much linked. So how we can study this these two processes? So that is also another questions that we like to study. But since the time is not enough, so I may not be able to discuss much about the last point, but I will discuss the first 3 points. Now, so this is just to show you how difficult it is, in what challenging environment generally we work. So this is the left figure shows the tower in Kaziranga, and the other 2 figure, it shows that particularly during the monsoon time, it becomes water inundation is a very common problem in this forest, and it becomes very difficult. In fact, during the peak monsoon time, that is July, August, it is we are not allowed to enter the forest, because whenever we like to go there, we have to approach the forest department, and they provide the armed guard, as you see here, because there are many animals. So without their support, and without that permission and support, we cannot go to the site. So, and because of this reason, generally monsoon time, almost every monsoon, we lose some data. So unfortunately, we lose some data. But the good point is that, so this provides the whatever data we get, so that is very, very, very valuable, as you understand that such kind of means in this forest is almost, there is hardly any human habitation, because it is a protected forest, and so there is no human activities allowed in this forest. This area is something about 864 square kilometer, so it is mostly pristine in that sense. So these are some of the wildlife which is seen in and around the tower where we have. Now, here I would like to show you the different biophysical parameters, and this will also explain why we get a different carbon sequestration pattern in Northeast India. For example, if you see the so this figure does not show the comparison, but what comparison of Northeast India rainfall and the rest of India rainfall. But what it shows here, the rainfall pattern in Northeast India. For example, the upper panel figure, it shows the monthly rainfall pattern for 3 years, 2016, 17, and 18. Please let me know how much time is left. Otherwise, I may continue for a long time.
Yes, sir.
Hello. How much time is left? This is almost 6, right?
Sir, yes, sir. So you can continue up to 6:15.
Oh, okay. So I'll skip some slides. So what you see here is that see in for example, January, February, March, we don't get much rainfall in most of the places in India. It is almost dry. But if you see in case of Northeast India, in February we get some rainfall, and in March the rainfall is quite significant. As you see here, this bar diagram, rainfall is sometimes almost 100. It goes up to 100 millimeter per month. And April it is much higher in the sense compared to rest of India. So because of this rainfall, early rainfall, this rainfall is mainly driven by thunderstorm activities, and most of this moisture comes from locally. That is because of evapotranspiration process. So this significant amount of rainfall, and secondly, you have also abundant radiation, because this is not the monsoon season. This is the spring season and the pre-monsoon season, where you have abundant radiation and then you have adequate rainfall. Because of these two environmental conditions, so this is the time when the plants grow at very fast rate. And as you know that Kaziranga contains a huge amount of biodiversity, like they have more than 2,000 rhinos and another probably more than 2,000 elephants. So they live on mainly wild grasses, and as per the this natural condition, this is the time when this grass they start growing. That is wild grass, because these grass are mostly seasonal. Unlike the woody plants, they live long years, but the grasses generally they start growing during the early year, during the February, March, and then after the end of monsoon season, they die. So they are completely dead. And generally November, December, they are completely dead. And lot of forest, because of forest, according to forest management practices, they are burnt. So these new grasses, they actually provide food to these wild animals. So, and this is a very interesting aspect of this forest. And Kaziranga, the grassland consists almost 60 to 61%, and woody forest is about 20%, and marshland is about 10 to 20%. So this is the how do they contribute in the Kaziranga ecosystem. So because of this significant amount of rain during the spring season and abundant radiation, the carbon sequestration process is maximum usually in the May. Generally there is a phase lag. So when it goes maximum, this is something about May. So this is the main difference with respect to the rest of India. Then this other parameters, it shows temperature, and the PAR is the photosynthetic active radiation, that is radiation component in which photosynthetic is maximum. So these are the parameters, environmental parameters, which control the photosynthetic process. And then last right panel, it is the LAI. That is LAI means that is basically sorry. So this is leaf area index. So how it is measured is that how much area of a forest is covered by, very roughly speaking, how much area is covered by plants and trees. For example, the value varies from 0 to 1. See, if you go to, suppose if you go to in desert, so leaf area index will be close to 0. And if you go to a very dense forest, so particularly where you cannot see the sun, so then leaf area will be close to 10. So this is how the leaf area index. So higher the leaf area index, so higher will be the denser will be the forest or the ecosystems that you can characterize. So now there are two components. So as I told you, there is a photosynthetic process and there is a respiration process. So imagine you are measuring the carbon sequestration on a diurnal time scales. For example, you are starting from 0, that is night 12, and then throughout the day, and next day night 12. So in that process, what you'll see here, that during the daytime, that is when you have sun, you have active solar radiation. So maximum amount of carbon dioxide is being absorbed by the plants. So this is what is denoted by this green thick arrow. So it is negative because it is coming from atmosphere and going to the plants. So it is negative, means it is acting as a sink. So in the right panel, what we see, so right panel actually it shows the diurnal scale variability, but it has been averaged on a monthly time scales. So we have some 3 to 3.5 years of data. So this data we have averaged on a monthly time scale. So it gives you a very good indication which month shows the maximum carbon sequestration. For example, we see May it goes about -20. So it has the maximum carbon sequestration capacity, but the month January and February, they have the minimum capacity. Now, but apart from this respiration process, photosynthesis process, you have the respiration process, which actually continues throughout the day and night. But daytime respiration process compared to photosynthetic process is very, very low. But nighttime you have the only respiration process. Hence, according to convention, so it is positive. That is, carbon dioxide is being released from biosphere to atmosphere. So it is shown by these two red arrows, and it is showing up. So if we combine these things, we'll get the total NE, that is net ecosystem exchange, which is shown here by this right panel diagram. So green means photosynthesis, that means carbon dioxide is being absorbed, and red means respiration, carbon dioxide is being released. Now, if we consider the total amount of photosynthetic, if we integrate this green area, so it will give you the total amount of carbon absorbed. And if we integrate the red, it will give you the total amount of carbon released. And if you do on a yearly time scales, then you can characterize the sourcing characteristics of an ecosystem. ecosystem. If green area exceeds the red area, the ecosystem will be characterized as a sink of carbon. But if red area exceeds the green area, it will be characterized as a source of carbon. So that is how we can characterize them. Now, here it shows the daily average of any GPP. So this is not very important. We can skip this slide. But consider this one. This panel, the lower panel, it shows the monthly sum of any. What I explained earlier, so that is the average value. But actually, we have to calculate by integrating the month wise, which is shown in this diagram. Now, if you see here, so we show here, for example, this continuous line, red line shows the RECO, means total ecosystem respiration, and GPP, that is total assimilated carbon, which is shown by this dark green line. So sometimes you will see that RECO, it exceeds the GPP, and in some cases GPP exceeds RECO value. So on an annual scale, what we have done in this case, we have seen here that GPP, at least in 2016, it shows the less value compared to RECO, and in 2018 it is marginally higher than RECO. So what we can say here is that in 2016, Kaziranga forest acted as a source of carbon, and in 2018 it acted a very mild sink of carbon. So this is in general the characteristic of carbon. If we consider all the 3 years, then we have seen that carbon sequestration potential of the Kaziranga forest is practically very, very small. So compared to other forests in India, it does not have that much of potential to absorb carbon dioxide. And what is the reason for that? So I'll come to the next. So this part I will skip, because this is related to isotopic analysis, and since I don't have much time, so I will better skip this slide. Now here it shows the soil CO2. I have shown you earlier that one of the sensors is there which can measure how much soil CO2 is being emitted, mainly because of the heterotrophic respirations, plus to some extent root respirations. So what we see here is that this left figure, it shows these 3 components. The continuous line, it is the NE, that is net ecosystem exchange, and the star line, the line shown by stars, it is actually soil respiration process. And total ecosystem respiration means soil respiration as well as respiration process by the plants. So this is shown by the dotted line. Now, what we see here is that if we see during the month of November, only the soil respiration, it is something about 2 to 3 in case of November. December is even less. Then from January, the soil respiration component increases. It is become sometimes, firstly it is about 2, then it becomes 3, then it is become 4 to April, it shows almost 5. That is, soil respiration process is almost 5 micromole per square meter per second. And the total ecosystem respiration, total ecosystem respiration goes almost about 5. So which is quite high compared to other ecosystem in India. And in the right panel, the lower light panel, it shows the monthly total above ground and soil respired CO2. What we see here is that we have only few months of data, because the reason being that, as I told you, during the monsoon time, it gets heavily inundated. And because in fact, in the earlier time, we installed one of the soil respired CO2 sensor, but we completely lost because of this, because of water inundations. So next time when we install this thing, so we generally take it out on the advent of monsoon, that is just before May or end of May generally, or early May, because it rains quite heavily in May also. So we put it up to April, and then we don't have any data for the monsoon season. But whatever data we have, this is very significant, and it shows that soil respiration plays a very, very important role in controlling the carbon dynamics of these systems. That's on the other hand, very simple word, CO2 respired by soil is very high, relatively very high. Even if you compare, we have measured the soil respiration process in Darjeeling also, and the daily scale, on a daily scales, the value at Darjeeling is almost half of that of Kaziranga. So that means Kaziranga ecosystem emits a huge amount of carbon dioxide because of soil respiration, and that is driven by the bacterial activities. Before that, before coming to BPD, I'd like to tell you one more thing, is that why soil respired CO2 is so high. One of the reasons could be that that Brahmaputra river, it flows across these ecosystems, and every monsoon it carries huge amount of sediment, and this sediment contains huge amount of organic matter. So when this organic matter is dumped, and eventually they get decomposed. So basically this organic matter comes from most probably out of the Kaziranga system, but they are being dumped at Kaziranga systems, and because of bacterial decay, so they emit huge amount of carbon dioxide. So this is one of the reasons why soil respiration is higher in Kaziranga. And then another reason is that is also a hypothesis. Hypothesis is that grasses, which comprises almost of 60% of the entire ecosystems, they generally die after the post-monsoon season, but their root remain for a long time. Their root remain long time alive, and then slowly they will also decay, but over a longer time scales. So when they decay, they will also emit huge amount of carbon dioxide. So because of these two reasons, the soil respired CO2 component is much higher in Kaziranga ecosystems than in most of the ecosystems in India. So that is one of the reasons, or main reasons, which actually makes this ecosystem is slightly it is as a source of carbon. Now this is one of the parameters, that is BPD, so which also plays a very important role in controlling the carbon sequestration process. Now BPD, it is the vapor pressure deficit. So this is a very important part. For example, if any of you have read botany, so you may be knowing that how this parameter is used to define the photosynthetic activity. So by definition, it is the difference between the amount of vapor in air or vapor pressure. Basically, the pressure of the vapor pressure in the normal air minus the vapor pressure when it is under saturation. So if when you take the difference of the vapor pressure of these two parameters, that is how much vapor is there at any given time, and then what is the vapor pressure if it is saturated. So this pressure, the difference will give you the VPD, and VPD is important. It is a better way to represent than temperature or humidity to explain the photosynthetic processes. So this VPD plays also a very important role. So I don't like to go in very detail about this figure because it takes some time. But what I like to tell you is that there is a if you see the diurnal variation of VPD, just like radiation, it actually increases, and then approximately at the middle of day it becomes maximum. But unlike radiation, the effect of VPD is not very symmetric with the photosynthetic process. For example, if you consider radiation, let us say at 7 o'clock photosynthetic process starts, when you have adequate sunlight and adequate temperature. Then approximately noon, photosynthetic process will be maximum. Then after noon, so radiation will decrease and photosynthetic process will also decrease. So it is more or less a symmetric process, almost you can say also almost linear system. But VPD, it is not necessarily a symmetric process, because there is a threshold VPD which will define up to a certain extent photosynthesis process will be maximum, and after the threshold value photosynthetic process will decrease. So what we have observed here is that this threshold VPD, sometimes it may happen, let us say sometimes it may happen in 1 year, on an average in 1 year it will happen earlier, and 1 year it will happen later. Now the year when it's happening later, so in that case photosynthetic process will be more, and in a given year when it is happening relatively before time, so in that process photosynthetic activity will be less. So exactly the same thing we have found in case of 2016, where the threshold VPD was obtained on an average. I am talking about statistically average value in 2016 it happened before compared to 2018. So 2016 the plants could not do photosynthesis as much as did in case of 2018. So this is also a process which determines the photosynthetic activity. Now this is the effect of rainfall. So what we like to show here is that the rainfall is higher. What we have done here is we have calculated what is the total amount of rainfall during the daytime. Throughout the day, 24 hours of day. What we have observed is that most of the time in case of 2016, the rainfall happened during the daytime. So what happens if it rains mostly during the daytime, the radiation is less because of more cloud coverage. But if it happens during the night time or evening time, but daytime is relatively free of rainfall, so you have more amount of radiation. But as well as you have adequate amount of water because it is happening during the night time. So what we have seen here, 2016 is characterized by more amount of rainfall during the daytime, and 2018 is characterized by more amount of rainfall during the evening or night time. So because of these two different environmental conditions, 2016 was less productive than 2018, and that is also made 2016 as a source of carbon and 2018 as a sink of carbon. So this figure shows we have taken different insets. I mean, in the inset shows different days. So we have taken we have considered few days, and we have plotted the diurnal variation of rainfall. And what I explained here, so that is what diagrammatically shown here. And this figure shows what is the different amount of this NE and GPP for different ecosystems. So what it shows here, for example, if you see the Kaziranga, Kaziranga shows the GPP value is about 2,100. But if you consider Betul in central India, so it is more 1,300. So in that consideration, so Kaziranga, the Betul forest, which is basically a teak forest, so it acts as a much better sink of carbon compared to Kaziranga. Similarly, if you consider another forest in Barkot in north India, so it also has more, it can absorb more carbon than Kaziranga. For example, in Barkot it is 2,900, and in Kosi Katarmal it is 2,400, which is almost equal to that of Kaziranga forest. So this is what the summary. So this figure actually what it shows here is that we have plotted the NE in this red line. It shows the NE on a monthly average. And the blue, this blue bar, it shows the monthly value of rainfall. So, and then this across the x-axis, so it shows the time axis. For example, in January, February, and November, December, they are winter time, and during the winter time, the photosynthetic activity is much less, and generally the greenery is lost, so they become dry. So which is shown schematically by this red or yellow color. And during the onset of monsoon, or basically during the springtime when it starts getting rain, so it becomes green. And then, so that is why March to September, October, it is totally green. And then photosynthetic activity picks up, and which becomes maximum during the month of May, which is shown here by the maximum NE value, that is maximum negative value. So this is schematically, this shows the carbon sequestration process in these forest ecosystems. So what we summarize here is that the maximum carbon sequestration during the pre-monsoon season, and the carbon sequestration process, it is weak, relatively weak compared to pre-monsoon season, but in the monsoon season it is relatively weak compared to pre-monsoon season, and subsequently it gets reversed. And then respiratory component is high, as I told you earlier, soil CO2 respiration is very high, which actually makes it is slightly carbon source process. And on an annual basis, the KNP ecosystem acts as a mild source of carbon. So this is my summary, and if you have now any questions, I'll be happy to answer.
Thank you, sir. Thank you so much. I would like to thank Dr. Chakraborty for such an enriching and interesting lecture. We will surely return from this day more knowledgeable than we got up today. So I would like to take 1 or 2 minutes break to compile the questions that we have received from the participants.
Okay.
Thank you, sir.
Okay. So we'll back in about a couple of minutes. So I'll now stop presenting.
Yes, sir.
Okay.
Okay, sir, that we have now received some of the questions. I would like to start the question answer session. Sir, shall I start? Hello, sir.
I think he's disconnected, or no, he's connected.
So I think he has muted his mic. Hello, sir. Can you hear us? So I think he will join us after 2 minutes.
Yes, we can wait for some time.
Yes, sir. Yes, sir.
Hello. Yes, you
Yes, sir.
You can ask
So shall we start?
questions. Yes. Yes. Yes, I am ready. Yes.
Okay, sir. Okay, sir. So for the first question, we have from Shoham Banerjee. How is the net ecosystem exchange affected by large-scale changes in forest tree cover, such as deforestation or earth flow?
See, net ecosystem exchange is basically it is the difference between photosynthetic activity and respiration process. So there is a two components of carbon. One is photosynthesis, the downward, and is carbon CO2 respiration is upwards. Now, if there is a deforestation process, so practically the photosynthetic process, say ideally, let us say a complete forest is removed. So what will happen? There will be no photosynthetic component. However, there will be respiratory component will still remain because you have soil, and soil, as I explained, soil respires a significant amount of carbon. So through the process of differentiation, so you are actually significantly increasing the carbon source to the atmosphere. So that is how deforestation process acts as a huge source of carbon in the atmosphere.
Okay, sir. And he also has another part, that is, how is the carbon which is sequestered by marine plants and sediments accounted for in NEE calculation?
Oh, that is a very interesting question. But marine process we cannot calculate using the eddy-covariance system. So that is, but through eddy-covariance we cannot apply this method in calculating the marine productivity. So that is a different techniques are used to calculate the marine productivity. So
Okay,
it
sir.
is in the terrestrial systems we measure both carbon as well as water vapor fluxes.
Okay, sir. Thank you, sir. For the next question, we have Shubhadeep Mukherjee, and he is asking that, sir, you mentioned that you do not collect data during the heavy monsoon season. So how does that affect your inferences? Is any
Oh,
adjustment performed to account for the missing data?
yes, this is also a very good question. And actually, the people who are involved, actually, they generally, they can also they can realize the limitation of these systems. So what we'll do here is that when we do partitioning, that is, any is partitioned into GPP and RECO, we must have data for entire 1 year. So whenever there is a gap, generally we do gap filling. So there are various statistical techniques. The gap filling can be done. Basically, you can say sort of interpolation process. It could be linear process. It could be non-linear process. So different kind of processes are there by which gaps are filled. However, there are certain conditions or limitations that if you have gaps for more than 40 days at a stretch, then these gap filling techniques won't work. So in that case, we cannot do gap filling for that particular year. So actually, we have data for 2016, 17, 18, 19. Of course, we have not completely processed yet, but what we have found is that in 2016 we have data almost for on 90% in 2016 and 2018. But in 2017 we have lost data for more than 40 days. So because of these reasons, we could not do gap filling, and we could not do the partitioning technique or this partitioning for 2017. But whatever data we have, that is also useful for particular that months. But gap filling technique cannot be applied when data is not available for more than 40 days. And though I have said that it is in monsoon generally we lose data, but it is not that entire monsoon data will leave. We cannot go or we cannot enter the park because of these environmental conditions and restriction by the forest officials. But generally data, these are all these instruments are all, they are all automatic instruments, and they generally work. Sometimes they fail also, but sometimes they work. So fortunately we get data at least 1 year. We have almost entire data during the monsoon time.
Thank you, sir. Thank you, sir, for the explanation. For the next question, I have a question that how small changes in rates of respiration from the breakdown of soil organic matter affects the changing climate and global carbon scale?
What is the rate of change in organic soil CO2 fluxes?
Yes, sir. Yes, sir. How small changes in rates of respiration from the breakdown of soil organic matter affects the changing climate and global carbon scale?
See, this is the question you have asked. It is basically one has to. This is a research question, we have not undertaken the kind of work we do. We cannot answer this question very quantitatively. For that, you need to see whatever we have done is soil CO2 measurements. We can measure. We have measured soil CO2 measurements. It is how much soil CO2 is coming out of the soil. But there are two components. One is the autotrophic soil CO2, and another is heterotrophic soil CO2. Autotrophic is purely by the plants matter. Let us say roots, and heterotrophic is by the bacterial population. So, in order to answer your questions, we must have a clear-cut idea or quantification of these two processes. That is autotrophic root respiration and the respiration caused by the bacterial population. So, for that you have to have microbial studies, microbial activities, microbial populations. So, those studies completely absent in our system. So that we could not do. So if we have these data, then only it is possible to tell quantitatively what is the, if this rate changes this much, so how much it affects the carbon sequestration capacity of an ecosystems. And then your question is asking on in general, probably applicable in a global scale, and that can be answered only when you have data. Ideally, supposing you have data from across the world, from several sites from the world, then you calculate how much change is there in the rate, and then in turn in the soil CO2 emission. So then only we can precisely answer this kind of question.
Okay, sir. Thank you, sir. So for the next question, we have Namrata Bishwash, and she is asking that how does genetic characteristics of a tree control the capacity of carbon absorption by a forest, and what type of forests will absorb more carbon?
Okay. The first question is genetic characteristics. So this actually I am unable to answer these questions because this is purely almost it is you need to have good understanding about the plant physiological process and plant genetics, which I do not have. So I cannot answer this question, but this is indeed a very good question. But second question is, which type of forest has a better capacity of carbon sequestration? So to answer these questions, what you have to do is that supposing if you compare the results from two different ecosystems, then you can get this answer. In my talk, I have briefly described about the carbon sequestration studies. This is in a Betul forest. It is in a forest in Madhya Pradesh, and that study is conducted by NRSC, that NRSC in Hyderabad, National Remote Sensing Center in Hyderabad, which is branch of ISRO. So they actually they carry out this kind of studies. One is in Betul and one is in our Sundarban. They have another tower in Sundarban. So in these two forest ecosystems they are doing, plus some other ecosystems. So recently they have published a paper in where they have published 9 years of data of Betul forest. Betul forest, it is the teak forest, and the forest what we do in Kaziranga, it is basically it is a deciduous forest. Deciduous forest or slightly semi-evergreen kind of forest. There is no teak tree here at all. But what we have seen here, its carbon capacity is much less. Or Betul tree, this teak forest, they have much higher capacity. So this is, to some extent, this is linked to your first question also. So teak forest has a much more potential to absorb carbon than the kind of deciduous forest we have in Kaziranga forest.
Thank you, sir. Thank you for the question and answers. For the next question, we have Shagnik Ghosh, and he's asking, how does the accuracy of these observations vary with change of time scales since the monsoon patterns are changing over the years? Also, do we have better results for observation throughout a year or through a decade or possibly even more than that?
Oh, that is also a very good question. Actually, the people who are actively involved this kind of work generally they answer they pose this kind of questions. So I wonder whether you are to some extent answer the person who is questioning this thing. So there are actually it shows a lot of seasonal variation. If we consider in case of Kaziranga, what we see here is that no, before that, firstly, let me answer these questions. What is the accuracy of this? So, see, for example, most of the people probably who are in geoscience, like geology and geochemistry, do. So, when you do any analysis using some instruments, how do you ensure that your data is correct? So, you do some kind of standard analysis, and then if you can reproduce these things when known value, so then you are quite sure that whatever your samples are also giving the good. For example, radiocarbon dating. How do you know that? Or any trace metal analysis, something like this. So you compare with your standard. But in this case, in these atmospheric measurements, we don't have such kind of system. So what we do here is that you generally, since we are measuring the energy components, for example, when you do this water vapor flux, we measure the what are the water vapor flux. We measure two water vapor fluxes. That is latent heat flux, and another is this sensible heat flux. So, and we get entire radiation, we get the entire energy received from sun. So, which is in one of the equations you remember, that is Rn. So, net radiation or the so-called global solar radiation. So, this radiation is being partitioned into two components, and one small component, of course, it is lost through the ground. So, supposing we subtract this component, so the net radiation received by an ecosystem is Rn minus G. Now, we are assuming that this entire energy is getting transferred in the form of water vapor fluxes, that is latent energy flux and this sensible heat flux, Le and H. So ideally Rn minus G should be equal to Le plus H. So this is your energy balance equations. When your energy balance equation is closed, that is left hand side is almost equal to right hand side, then you can assure that your measurement is pretty good, is pretty precise. But in reality, probably nobody gets this kind of completely closed equations. So it is about, but if you get up to 80%, then you can make sure that your measurement is pretty good. Why it is 80%? As I told you, that there are certain limitations. For example, the instruments generally they measure at a very high frequency, a 10 hertz frequency. So every second you are measuring 10 times. Why it is so? Because of the small eddies. So you have to characterize the eddies because they are so small and they are so fast. So you have to make very high frequency measurements. But even then, it may not be possible to capture each and every eddy. So some eddies will be lost, and measurements is out of the capacity of the instruments. So because of these reasons, actually these fluxes are always underestimated. And secondly, you don't get exact energy balance closure. That is because some of the energy we cannot measure. That is, for example, every canopy, they have their own heat storage. For example, we have our own temperature, body temperature. Similarly, the forest ecosystem, if you consider aggregate system, it will have some temperature. So it will have some energy. That energy we are not measuring. Then, supposing you have in particular system, you have lot of liters. The liters are falling and they contain a lot of water also. Particularly in rainforest, you have lot of liters, leaves. So they contain a huge amount of water, and they also release in the water vapor flux. So those things we are not considering. So because of these unaccounted components, we do not get exact energy balance closure. So these are the reason. So we generally underestimate. And the secondly, how does it vary from season to season? That is that in answer this question, we have to do generally we do on 4 seasonal basis. That is monsoon, post monsoon, winter, and pre monsoon. So during these 4 seasons, what we have found in case of Kaziranga, pre-monsoon has the maximum carbon sequestration capacity. That is, the productivity or the carbon sequestration is maximum during the pre-monsoon season. And because of this reason, the energy balance closure is the best in pre-monsoon season. Whereas if we go to winter season, the energy balance closure is the least, and the carbon capacity also less during this time. So they are completely coupled. So this is how you can understand how it varies from season to season, and how the accuracy of the or the precision of the measurements, how it varies also from season to season. So does it answer your question?
Yes, sir. Definitely, sir.
Yeah.
Thank you, sir, for all these answers. Due to time constraint, we have to wrap up the session for now. So before calling for the vote of thanks, I would like to request our respected teachers if they want to say something for such an enhancing talk that we have just witnessed. Sir?
Yes, please. Yes, can you? Sorry, can you tell me? You are asking me to tell something?
No, sir. Sir, I was asking our teachers.
Yes, I will request our present head of the department, Professor Orijit Rai, to say something and conclude the session.
Well, first of all, I'd like to thank Dr. Chakraborty for this nice and very lucid talk. On behalf of Geological Institute and our Department of Geology, Presidency University, we all congratulate you for your nice work and hope you will continue with this type of work, which has relevance to our society and global climatic conditions. Thank you, Professor Chakraborty.
Most welcome.
Thank you, sir. Now I would like to ask Shayantika Ghosh for delivering the vote of thanks on behalf of the committee members to our speaker for this precious time that he gave us. Please take over the mic.
Thank you, Ritanuka. Good evening, everybody. On behalf of the Geological Institute, Presidency University, I would like to thank Dr. Supriyo Chakraborty, sir, for this incredible session. It is not every day that we find the opportunity to be enlightened by such an illustrious personality. We express our heartfelt gratitude, sir, for taking out time for us from his busy schedule to grace this event. Thank you, sir, for such an informative lecture. We are eager to maintain this relationship in the future and have you with us for such sessions. Since you are in Kolkata, we would like to take this opportunity to invite you to visit us at the Department of Geology, Presidency University, whenever you find time. I would also like to extend my heartfelt thanks to all our faculty members. Last but not the least, I would like to thank all the participants for their unwavering support and active contribution in making today's session successful. We promise to come up with a lot more of such informative webinars where we get the chance to interact with such eminent academicians from all over the world. Before you leave, I request all the participants to kindly turn on their cameras for a while so that we can take a screenshot and preserve the moment.
তোমার ভিডিও অনই আছে।
Thank you, everyone. Let's call it a day for now. And for anyone who joined late or wish to look back upon this lecture, you shall find the talk on YouTube channel. We hope to see you all very soon. Till then, adieu, stay safe, and have a great weekend. Thank you.
Just like to say, Professor Chakraborty, make a program of coming to the university on 1st December. See if you can get time. Inform us
Yeah, of course,
one or
of
2
course.
days before.
Yes, surely. I'll try to come on first.
Yeah, please try.
Yes. Okay, bye.
Thank you, sir.
Thank you.
Most welcome.
Thank you, sir.
Welcome.